Let's talk about instantaneous acceleration. So for instantaneous acceleration, you have no subscript AV down here. You just write A with a vector sign on top. And again, when we talk about instantaneous, we are limiting ourselves to a very, very short moment of time. So what we do, we take the equation for average acceleration, then we limit the delta t here, we limit it towards 0. How do we limit this mathematically? What we do is we introduce a limit notation. So this limit notation will restrict delta t towards 0, and with that restriction, we are studying only the change in velocity that happens within a very, very, very short window of time. So if you change it into symbol, this change here is represented by the symbol delta. Okay, time duration is basically the final moment minus the initial moment, right? So it's also a change in time. So this one is delta t. So once you have delta v vector divided by delta t, we can change the delta to become d. Okay, because delta is a finite change, d is an infinitesimally small change. So when we limit the delta t to approach 0, we are technically asking for an infinitesimally small change. So we can change this to become dv over dt. Again, this is a vector, so since this is a vector on top, your acceleration here will be a vector as well. Okay, so let's say we want to investigate the instantaneous acceleration at time equals to 7 seconds. At the 7th moment where the time is 7 seconds, we want to investigate the instantaneous acceleration. So what are we actually doing mathematically? We are finding at this moment within an infinitesimally small duration. Let's say from 6.999999999 to 7.000000000, that very, very short moment, right? Initially you will have a velocity. Finally you will have a velocity. Okay, initial here means by 6.999999999, a lot of 9. Then final will be 7.0000000 and a lot of 0 behind. So within that short moment of time, there will be a change. Okay, if accelerating or decelerating, you will have a change in your velocity, initial and final. So if you take the final minus the initial, then that is the dv that we are asking for. Mathematically, this one cannot be measured. It's a mathematical idea. Okay, so if your final velocity is larger than your initial velocity, then you get a positive dv. But if your final velocity is smaller than your initial velocity, then you get a negative dv. Quite straightforward, right? Okay, so that's the idea. Once you get that change in velocity, you divide by the infinitesimally small change of time, then that's how you get the instantaneous acceleration. Okay, but again, since this is a vector, right, to multiply to divide, you cannot do it with the direction. So in order to take into account the direction, we do resolve. Okay, resolve into x and y, but here everything is in x direction, so we only resolve to the x component. So if you do it to the x component, then you'll be x component of acceleration equals to change of the x component of velocity over time. Okay, dvx over dt. This is in the x component. Of course, you can have y component, then it's ay equals to dvy over dt. Okay, so this is a mathematical idea of acceleration.